Uh, Last day we have discussed the coding behavior in terms of state transition diagram. So that was Xn and two outputs. Xn is the input and output behavior of the convolution coding diagram. So the convolution, of course, in the digital domain can be implemented using simple shift register. So that means whenever I give a input here and on the next clock, actually it will be shifted, Mn will be shifted to Mn minus 1. And while it is getting shifted, the output will be generated. So that way the state transition diagram was constructed, that is the input and corresponding to outputs. So whenever there is a change in state, it will corresponding to an input bit. So there will be two outputs, two parity bits will be output, and correspondingly there will be a change in state. Now this one can be tracked because here it is in a circular fashion. Now to make a trellis diagram, usually we require an initial state. So that is the first assumption. Initial and final state are assumed to make the trellis diagram. Usually they are made 0, 0. However, depending on the situation and kind of implementation of this convolution coder for a particular device behavior, people use any input they desire. But conventionally, the input, the start and finish at the start and at the end the states are taken to be 0, 0. So with that, the trellis diagram is made. So on the left side, we have the 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. So these are the 4 states which has been made by the state of, the shifted input, that is whatever be the current value of x minus 1, n minus 1 and x n minus 2, that gives the state. And then we have the output also. Depending on the number of message bits, actually we can make this output as long as possible. There could be hundreds and even thousands of bits are used as a one serial stream. So in that case, this length could be up to 1,000 stages or few thousand stages even it can go, because convolution coders are used for in communication in gigabits per second also. So therefore, this can go quite long. However, here, for example, we will use it relatively small number. So let us one stage here. Then next stage would be 1, 2, 3, 4, 5. Let us make. So this is the start and this is the finishing. So the diagram can be made adaptive by making the start and finish variable, but usually the start and finish is taken as 0, 0. So now, so this is all whatever be the, whenever there is an input bit, there would be, say, change of state. Okay. So correspondingly, there can be, because it is a binary system, there can be two possibilities of input. One can be 0 and another can be 1. So if it is 0, then of course it will give 0, and there is no state change. So there, if it is 1, then what will happen? If it is 1, then it becomes 1, 1. No, from 0, 0.
Sir, in this diagram, how are we deciding the parity bit outputs?
Parity bit outputs are basically, suppose there was 0, 0. If I give a 1 here, this was 0. Okay. And this was 0. Now we give a 1 here. So 1 has been given. So if I give a 1, then this 0 plus 1 would be equal to 1, and then 1 plus 0, that will be 1. Okay. So that means this parity bit will be equal to 1, and this will be 1 plus 0. This will be also equal to 1. Is it right? Am I doing mistake or what? If I give a 1, this, I could say 1 here. So first one, then this is the convolution operator of 1, 1, 1. This is the convolution operator corresponding to 1, 0, 1. So if I convolute 1, 1, 1 with the first bit 1, so the first will be 1, but next should be, this is 1, 0, 1. This also, if I fold and if I convolute with the input, so that way also it becomes like if we do this convolution, so then also this is 1, 1, 1 and 1, 0, 1. We have the first one is suppose 1, okay. So then what will happen? Then our first output will be equal to this x0, 1 is 1, okay. What is x2, 1? X2, the first one is 1. So therefore both are 1 in this case. The output will be 1, 1, okay. Now giving the output 1, 1, where it will go? Sorry, it will go to 1, 0, okay. Because next state, first shift, this was 1, next clock this will be equal to 1, this will be equal to 1. While this becomes, the output becomes 1 and 1, so this also becomes 1. This goes to 1. But this becomes, this is still 0. So therefore, the next clock, the output will become 1, 1 and the state becomes 1, 0, because state is defined by the change of this set register output, that is the values of xn minus 1 and xn minus 2, okay. So this remains 0. Next clock only this will become 1, okay. So therefore, if we have if we give an input 1 while this was 0, next case this will become 1, and the output, while it becomes 1, the output, these two parity bits is the outputs from the two convolution generators. Convolution generator in binary form is nothing but an XOR gate, okay, and passing through a shift register is the shift. So therefore this becomes a simply 1, 1, okay. So the output becomes 1, 1. And the state becomes 1, 0. State becomes 1, 0. So while it gives the output, state is here. So this is the 1, 0. So it will come to this one. For an input 1, it will give output 1, 1 and come here. Okay. So all those blocks we have to draw, or this can be these are all states. and every stage, that means every time instant as it proceeds, there will be a change in state, and there is a possibility of two types of change corresponding to two types of input. So these all are 1, 1. So if I have, so corresponding to that, this will come, and next, of course, every time we get a 1, 0 here, it will go like that. And if we have a 1 here, it will come to this place with 1/1. All these are states. All these are states. Okay. So now suppose here also from 0, 1, if I put a 0, then if I give an input 0 to this while the state was 0, 1, so then it gives output 1, 1 and go to the state 0, 0. On the other hand, if we give 1, it gives output 0, 0 and goes to 1, 0. Similarly, for 1, 0 also, for 0 it goes to 0, 1. With an output of 1, 0, and for 1 it goes to 1, 1 with an output of 0, 1. So this is the first stage complete, and horizontal and vertically. And here also, if we from 1, 1, if it is 1, it is 1, 0, it remains set there 1/1, 0, 1/1, 0.
So it will have to be 1/1, no?
Yes, 1/1, 0. It goes to the state 1, 1. It remains in the state 1, 1. Now, if we give a 0, it will change a state. It goes to 0, 1. Everywhere it will be same. Okay. So from 1, 1, these are the changes. From 0, 1, of course, we have 0, 1, also similar thing will happen. It will goes to 0, 0. By giving an output 1, 1 and 1, 0, 0. Zero slash 1, 1. 1 slash 0, 0. Similarly, for 1, 0 also same thing. 0 will give 1, 0 output and goes here. And with 1, it comes to 1, 1 state, giving an output of 0, 1. So this is the 6-stage trellis diagram. So basically this is to track all the state changes corresponding to every stage. Stage means with a new input, the a new stage will come. Like say how if we want to transmit a bit, like say 0 here. Transmit a bit 0. So message 0. So message 0. So therefore 0 input, there is output will be 0, 0. So the code will be 0, 0. So next bit is suppose 1. The code will be 1, 1. This is the output. So, but after this one, there is a change of state. Okay, there is a change of state. So now we are here.
Sir, how can we say code for message 0 is 00?
No, because input is 0, and our assumption was there because this is an assumption. Conventionally, at the start and at the end, the states are taken as 0, 0. So we have taken that initially start is 0, 0. So this is 0, 0 actually. Otherwise, suppose we have the starting point is 0, 1. Then with a 0, the output would be say 1, 1. Then the code would have been 1, 1. If the initial state was 0, 1. So it will depend. So the code will completely depend on the initial state. The initial state will determine the code. So therefore, most of the time, a fixed convention is chosen for a series of bit stream. But to do that, usually what have to be done, say, I am 1 kilobyte stream I am transmitting in as a one sequential convolutionally coded bit stream. Then this to make this initial states 0, 0, that shift registers values need to be reset. We have to press because that's a digital circuit. We have to give the reset. So therefore, that will become 0, 0. So from that, again, a new code will start with initial state 0, 0.
Sir, after 0, the message is 1. So that means this 1 corresponds to the input. So whatever is above the slash,
Yeah,
that corresponds to 1.
Yeah, this is the input message actually. Input message are coming. So first it has come 0. So there is no change of state. Okay, it is still 0, 0. So these are all 0, 0 state. There is no change in state. So now, so therefore we have gone here. There is no change in state with the first input. Okay, but next message is one, message bit is 1. So with that, actually, there will be a change in state. And while it is going from 0, 0 to 1, 0, it is giving the output 1, 1. So this will be the coded message. So the coded message corresponding to the bit 1 after 0 is 1, 1. So see that it depends on the previous bit. Because here the next bit is suppose another 1. Okay. So then we have to trace it here because now we are here. So from here, if we give a 1, what will happen? If we give a 1, it will come to this state with the output of 0, 1. So therefore, this code will be 0, 1. So next, suppose another 1. So we are here. So with a 1, it will remain here with the output of 1, 0. So it will be 1, 0. Next, suppose we have 0 here. And so here we are here now. So now with a 0, there will be a change in state. So with a 0, there will be 0, 1 would be the output, and it will go there. So 0, 1 is the output. So the code will be 0, 1. Now suppose we have another 0. from 0, 1, if it goes to 0, so it will be 0, 0. So generally another terminating 0, this is used either, in this case the message was having 0. Otherwise, generally a terminating 0 is a terminating bit is used to refresh this, or otherwise it has to be reset to 0, 0 for the to prepare for the next stage. So therefore, the trellis diagram, if we trace, so this is the path that is coming into picture. Okay. So this way it is moving. The coding process is moving in this fashion. So this and the coded message 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1. Now the decoding process. Decoding process would be simple. First, we have to take 2 at a time. Okay. So now suppose we have to see that where we are. So this is the code we have received. We have received the code 0, 0. So the message becomes 0 with the initial state 0, 0 with 0, 0. This is becomes 0. Okay. Now next coded message is 1, 1. Now we have to check from this 0, 0. There could be 2 outputs. So there could be 1, 1 and 1 like that. However, to trace like this, we are assuming that everything, there is no error. If there is an error, what will happen? If there is an error, suppose there is an error, then we have to decoding can be done easily by tracing the trellis diagram if there is no error. In case of error, usually we have to take a distance measure. Distance measure in binary code, the distance measure we take is the Hamming distance measure. That is the difference between the number of ones of the 2 codes. Closest correct code. And the corresponding . However, here also there is a limit, the number of bits that could be corrected, like before, like the other cases here also. There is a limit on the number of error bits. Which depends, or depending on the minimum intercode distance. The bit error, number of bit error would be the minimum distance minus 1. Because in Hamming distance, in case of binary numbers, would be integers. So therefore, the distance will be just, if it is 3, we can correct 2 bits. If it is, say, minimum is 2, then we can make it 1 bit error corrected. Generally, for a long, but the problem is that to find this optimum or minimum error code from computing distance of all combinations takes a lot of time. For a longer bit stream. It may become computationally expensive. To find the minimum mean distance code, correct code. In the likelihood sense. So which is known as the maximum likelihood. We have to maximize the likelihood by minimizing the distance. Now, so Viterbi proposed a method to reduce this. To reduce the computational burden. Viterbi proposed the piecewise search. Maximum likelihood search. So the essence of the algorithm is that is to find all optimum paths to the next state. optimum path. Next state from the current state. And store them. If they are optimum, we store them. And then next stage, start with all optimum paths in the previous stage. Up to current state. And evaluate to the next stage. So this is basically part by part search. So every time we store all the optimum paths, and as we proceed, some of the paths will not be optimum. Some of the paths will not be optimum. As this can be explained, I will just explain with a simple example here. Suppose, let us take the same example. Let us say that there is a code, received code is in error. Received code is in error, and that has been received as 0001 01 10 01 10. So now 00 is fine. Okay, so 00 there is we pick the 0. All right. So then we have suppose 01. However, 00 there is a valid code. Okay, so the first bit is 0. So therefore this is okay. So this gives 0. Now we are here 00, but there is no output 01. Okay, so this one is 00 and this one is 11. So how can it become, if preceding code is 00, it cannot be 01. It could be either 00 or 11. All right. So but it is it has been received 11. So then we compute the distance, Hamming distance. However, in this particular case, the Hamming distance is also 1. So therefore, both will be there. So we have here, then this is also there, and this one is also there. Okay. So both are there. And the cost is, of course, in this case, Hamming distance is 1. So cost is, here also cost is 1, here also cost is 1. Okay. Next, what happens? Next, we have 01. Now, if it is again, there is no 01 here. So here the cost was 1, Okay, here again 0, 1 is not there. So again plus we have 1 plus 1 because 1 cost is there. Now from this one, do we have 0, 1? Yes, we have a 0, 1 here. Okay, so this gives either 0, it could be either 0 or 1 for this 0, 1. Either 0 or 1, because here if input is 1, it will trace this path. If input is 0, it will trace this path. And the code cost, code distance from the valid code is same. So therefore it could be either of them. Okay. So at the next stage, what is happening? So we have here, we have come to this stage. Okay. So this becomes, again, it could be 0, 0. Okay. So 0, 0. So then this cost becomes 1 plus 1 because there is no 0, 1 is here. Now at this stage, if we are here, so this will be the 0, 1 path. Okay. So this distance remains same. So therefore this will be nullified, and because this becomes okay, and then this is also okay, the previous path. So these two will be nullified. So now we are here. Okay. So therefore this will not be the valid one. So it will be 1, and correspondingly we will have another one. So 1 is this becomes 1 at the next stage, and this one becomes 1 here. So like that it will proceed. Now here of course 1, 0, 1, 0 from here we have 1, 0, 1 valid code is there. So we go to with 1, is input is 1, so the input is 1. So now we are here. So at this place, again, we have to see that what are the valid outputs. So the valid outputs are 0, 1 and 1, 0. So valid output 0, 1 is there. Okay. So therefore, and that corresponds to 0. So that corresponds to 0. So we go there. And then we have, again, we have 1, 0. So there is no 1, 0. There is no 1, 0 at this place. However, the distance are same. It could be either to this place giving output 0, 0. Okay. That is corresponding to an input 1, and this can be corresponding to an input 0. It can give output 1, 1. So the distance of 1, 0 from 1, 1 and 0, 0 are same. However, because this is the final message and we want to know that this is the initial stage, our final state is 0, 0. We'll take this route and then we will put the message 0. So that way, this is the decoding. Piecewise decoding can be done. So this is known as precisely the decoding part. The essence of Viterbi decoding is that each stage we search for the optimum paths corresponding to this distance criteria, and that optimum path is based on all previous cost to this point. So like here we were tracing that all previous cost, this cost was 0, this cost is 1. Now correspondingly here another 1 cost is, so this cost becomes 2, whereas this cost becomes 1 because this added cost is 0. So therefore, we have chosen this path. So the same code can be recovered by computing the minimum Hamming distance of all possible codes as well. So this is a 6-bit message. So if we take the all possible combination of codes corresponding to various 6-bit messages and compute the Hamming distance, we will find that if we compute the minimum Hamming distance, so we will also come into this conclusion. However, that way that becomes computationally expensive, especially where the number of bits increases. That is, corresponding to the number of message bits, number of stages will increase. The search also become complicated if number of convolution generator also increases. In that case, here our state is of only 2-bit stage, 4 stages, 4 states are there. But in case number of generator increase, this will also increase. So this is, I think with that, there are another technique is also there based on tree search algorithms. We will not discuss it further. With that, we shall stop at channel coding, though there are many other channel codings are there, like more efficient channel coding, which are also available. Some of them known as BSC code, and another is Turbo code is also there. But I think that this is enough for our discussion with channel code. Next we will discuss, next day we shall start with line coding. Because now we have completed source coding and channel coding. After that, we are here. After that, we are going to analog front end. So before going to that ASK, PSK, FSK modulator, usually there is one stage that is called line coding. So line coding essentially means that generally for when we conventionally take 0, 0 means near 0 voltage, and 1 means generally some plus V or plus 5 volt, or plus 2.5 or plus 0.5, something plus volt, plus V volt. Now, however, it has been seen for transmission that usually this is not the most convenient way of coding or sending the analog signals in distortion-free manner. So therefore, an appropriate line coding or analog voltage coding would be there. So that means one popular example is polar coding. So that means 0 volt actually has an uncertainty that that signifies cannot be guaranteed always. Detection may not be guaranteed always, can be confused with noise, etc. So therefore, in some code, say plus 1 is represented by plus 5 volt, then 0 is represented by minus 5 volt, like that. There are other codes where a different perspective is also taken. Before going to FSK, ASK, all kind of modulator, in the digital domain itself, the bit to analog voltage definitions are usually done in a particular manner to reduce the error and the bandwidth requirement. So we shall discuss a little bit of both from next day. And maybe I will give some practice problem tomorrow, or tomorrow I will give some practice problem. The test